All right, kids, we're going to look at reactions homework number 2. It's in this pack, and it's near the back. It's called single replacement reactions. You need to take this out. You're going to need a pencil. You're going to need your reference table, and you're going to need your periodic table. And balancing equations is not the easiest thing in the world. We have to practice it, and mostly the problem that you're going to have is not writing the formulas correctly. If you don't write the formulas correctly, you're not going to be able to balance it. It's going to be wrong from the start, and you're going to have to, I'm going to try to get that light out of my head. You're going to have to, you're just not going to be able to do it. So here we go. You're going to have to write a balanced chemical equation for each of these. You got to use the phase symbol, solid, liquid, gas, or aqueous. Now, if it's a solution, it's aqueous. That means it's dissolved in water. Metals on the periodic table are always solid unless they're mercury. Mercury happens to be a liquid. Very few other things happen to be liquid. Just bromine, actually, is going to be a liquid. An ionic compound can't be a liquid unless literally it's thousands of degrees. So that's not going to be a liquid. Any ionic compound will not be a liquid in any kind of normal situation. And the gases, you're going to have to get used to them. Gases are gases, and some things are gases, and some things aren't. I'll talk you through them. Just try to remember them. Okay? Phase symbols are not the end of the world, but they're important. Now, if there happens to be no reaction, because sometimes you put stuff together and there is no chemical reaction, you would then write the letter X or X with no reaction, X in the words no reaction. You'll see how that looks coming up. In some of these, there'll be no reaction. But you have to write the symbols for the reactants. It's practice writing formulas. So you will write the formula. Don't just write no reaction. You'll actually write the formulas for the reactants, and then after the arrow, there would be no reaction. You'll see how that looks. Here we go. In the very first one, I'm not going to read all that stuff at the bottom. I'll talk through a lot of it, but you can read it or pause it or whatever you want. In this reaction, we have zinc reacting with hydrochloric acid. Hydrochloric acid has a formula of HCl. All acids are aqueous. Zinc is a metal. Zinc is a solid. It goes into the acid. This is the setup for a single replacement reaction where we have atoms that go into an aqueous solution. You have to look at table J. Now, out of the 3 parts, zinc, hydrogen, and chlorine, 2 of those 3 parts are going to be on one side of table J or the other. Whichever one is higher goes into solution or stays in solution. Now, as it turns out, zinc and hydrogen are both on the left side. Hydrogen is not a metal. See at the very bottom of the table where it says hydrogen is not a metal, but hydrogen compounds can make acids, which can give you H+1 cations, just like the metals make positive cations. So the zinc and the hydrogen, the zinc in this case will replace the hydrogen because zinc is higher on table J. Zinc is more reactive. So when we replace the zinc in solution, right, zinc is higher. When we put the zinc into the solution with chlorine, zinc makes a +2 ion. Put your finger in box number 30 on the periodic table. Zinc makes a +2 ion. Chlorine, element 17, makes a -1 ion. When you crisscross, it's ZnCl2. Hydrogen, when it gets bumped out, hydrogen's a Hunkelbrief twin. When it's pure, it's H2. In the compound HCl, hydrogen and chlorine are both Hunkelbriefs, but not when they're HCl. They're a compound. They're not pure hydrogen or pure chlorine. In zinc chloride, chlorine happens to be 2 chlorines, but not because it's a Hunkelbrief, but because zinc is a +2 ion. This is the skeleton. Zinc and hydrochloric acid will form into zinc chloride solution and hydrogen gas. Now, in a single replacement reaction, whenever we start with an aqueous solution, we always end up with a different aqueous solution. Soon, I will show you how to look at a compound and decide, will it dissolve in water or not? Will it be aqueous or not? For single replacement reactions, if the reaction occurs, if the atoms are higher than the ions and it occurs, we're going to have another aqueous solution. So to balance this, you have to start talking yourself through this. Say it. Say it with me. There's 1 zinc on the reactant side. There's 1 zinc on the product side. That's good. Next up, hydrogen. We have one hydrogen on the reactant side, but we have H2 on the product. That's not good. In order to fix that, we have to put a 2 in front of HCl, and then we have to start all over again. So here we go. There's the 2. We start over. There's one zinc in the front, one zinc in the back. That means reactant and product, front and back. There's 2 hydrogens in the front. There's 2 hydrogens in the back. Now we have 2 HCl's. That means we have 2 chlorines in the front and we have 2 chlorines in the back. Now it's balanced. This is balanced in a 1 zinc plus 2 hydrochloric acids makes 1 zinc chloride and 1 hydrogen. It's a 2 to 1 to 1 to 1 ratio. John Dalton said things happen in simple whole number ratios. 1 to 2 to 2 to 1 cannot be reduced. Whenever you finish balancing an equation, check the ratio. Because if you happen to get lost and keep building and building and building, you might end up with a 2 to 4 to 2 to 2 ratio. Now that would balance, but it's not correct. It has to be the lowest possible ratio. Number 2, iron Roman numeral 2 nitrate solution plus silver metal. Iron Roman numeral 2, put your finger in box number 26 for iron. Iron makes a positive 2 ion or a positive 3 ion. Here it's positive 2. And if it's positive 2 and nitrate's in negative 1, nitrate's on table E, we're going to get Fe, and then NO3 is in parentheses doubled because it's a plus 2 and a minus 1. Silver, element number 47, is a solid because it's metal. Now we're going to go look at table J. Iron, nitrate, and silver. 2 of those 3 things are on the left side of the table, the metals, iron and silver. Nitrate's not even on the table. That doesn't matter. We only need to have 2 items on one side of the table or another to decide what happens. And in this case, when we see that iron is actually higher than silver, silver jumps into the solution and says, yo, I want to dance with the nitrate. And iron says, you can't push me out of solution. You're lower on the table. You're less reactive than me. So here we're going to have what's called no reaction. And see, you put an X and the words no reaction, or even just the X, or I guess even just the words no reaction. You have to write the symbols for the reactants. And then you write, nothing happens. Don't be switching stuff. Don't write silver nitrate and iron and then no, that doesn't happen. This literally doesn't happen. No reaction. Number 3, fluorine gas is mixed with sodium bromide solution. Fluorine is a Hunkelbrief twin. So when it's pure, it's F2 and it says it's a gas. So put in a G. Sodium bromide. Sodium is a positive 1 ion. Bromine is a negative 1 ion. That's element number 9 for, element 11 for sodium and element 35 for bromine. Positive 1, negative 1, 1 to 1 ratio. And it's aqueous. It says it's aqueous. So we put in it's a solution, AQ. I will show you soon how to know that it's aqueous, but it is. Now, it's the perfect setup for single replacement reaction. We have element atoms, they're diatomic, fluorine, and it's going into an aqueous solution. So, in this case, fluorine is higher than bromine. This is actually going to happen on the other side of the table, on the right side. Fluorine is higher than bromine. So here, the fluorine will replace the bromine in solution, and the bromine is going to get bumped out. So this is how we write the skeleton. It's the fluorine, which is diatomic, goes into the NABR aqueous. That's in a 1 to 1 ratio. It's going to form bromine, happens to be a liquid. Right? I told you that before. Bromine and mercury are the liquids. Br2, because it's a Hunkelbrief twin. Now, when sodium fluoride forms, that's because the sodium stays in solution and the fluorine here is going to replace the bromine. It used to be NaBr. Now it's going to be NaF. Fluorine makes a negative 1 ion. Sodium, of course, is still a positive 1, so it goes together in a 1 to 1 ratio. And that's going to be aqueous. So now we have to start balancing by talking to ourselves. Balance it. Talk to yourself. Ready? There's 2 fluorines in the reactant, but there's only 1 fluorine in the product. To fix that, we have to put a 2 in front of the sodium fluoride, and we have to start over. So by putting a 2 at the end there, we start talking to ourselves again. There's 2 F's in the front. There's 2 F's in the back. Good. In the front, I have 1 sodium, But in the product, I have 2 sodium fluorides, 2 sodiums. So in order to fix that, I have to put a 2 in front of the sodium bromide on the reactant side, and I got to start all over again. So I put a 2 there, and I start again talking to myself. There's 2 fluorines in the front. There's 2 fluorines in the back. There's 2 sodiums in the front. There's 2 sodiums in the back. There's 2 bromines in the front. See, 2 sodium bromides, 2 bromines, and I got Br2 is balanced. This is in a 1 fluorine to 2 sodium bromides to 1 bromine to 2 sodium fluorides, 1 to 2 to 1 to 2 ratio. John Dalton's happy. I'm happy. You should be happy too. This is a balanced single replacement reaction. This happens to be called an anion replacement because the fluorine replaces the bromine. Most single replacements are actually cation replacements because the metals replace the metals in the front of the compound, but this one happens to be an anion replacement. Gold Roman numeral 3 chloride. So put your finger in box 79. Gold makes 2 different kinds of ions, and I'm looking at them over there, +1 and +3. Roman numeral 3 means gold +3. Chlorine is element 17. It only makes a -1 ion, so gold chloride, gold Roman numeral 3 chloride, is going to be AuCl3. And magnesium is element 12. It's a metal. So this is how we set it up. AuCl3, it's aqueous. It says solution, so it is a solution, aqueous. And magnesium's a metal. So now we go to table J. We have 2 metals, gold and magnesium. They're probably both on the left, and they are. And chlorine's on the right. But we only look at the side of the table where 2 items are, not 1. And when we look, we see that gold and magnesium are both on the left, but magnesium is higher. Gold is lower. So the magnesium is going to bump the gold right the heck out of solution, and the gold's going to literally fall out as solid gold, as a metal. So when we switch this, the magnesium hooks up with the chlorine, and the gold pops out. Now, this is something that's really important. When you switch them, right, that's what we did. We switched the magnesium in and the gold out. Magnesium, you have to check. Magnesium makes a +2 ion, and chlorine's a -1. So the formula for magnesium chloride is MgCl2. Now we had AuCl3. Gold has a +3 ion, so you need 3 chlorides. Magnesium's different. Magnesium's a +2 ion. You only need 2 chlorines. That means we have different formulas, different numbers of chlorine. It's not balanced. You have to write the formulas correctly. If you got lazy and just said, well, I'll just make it MgCl3, well, it'd already be balanced and it'd be already wrong. You have to write the formulas correctly. You cannot assume that there's 3 chlorines in gold, that there's going to be 3 chlorines in everything. Sodium only gets 1 chlorine. Magnesium gets 2 chlorines. All right. And there are plenty of elements like, let's take a quick peek. Zirconium would get 4 chlorines, or vanadium could have 5 chlorines, and chromium could have 6 chlorines. You have to look to see what kind of cation forms to write the correct formula. So this is the setup. This is the skeleton. Now we have to talk our way through balancing. So we're going to say it. Ready? There's 1 gold in the front. There's 1 gold in the back. Good. There are 3 chlorines in the reactant side, but there's only 2 chlorines in the product side. Now 3 and 2 is even and odd. Actually, it's odd and even, right? There's 3 odds and 2 evens. The odd one is broken. That's our mantra. Our odd one is broken. The odd one needs to be doubled in order to make it even. And then we have to start all over. So the only way to get an even number of chlorines in the front is to put a 2 in front of the gold Roman numeral 3 chloride, and then we start over again. So watch. I got a 2 out front, and now I'm going to start talking to myself again. There are 2 golds in the front, but there's only 1 gold in the back. In order to fix this, I have to put a 2 in the back, the second gold, and I have to start all over again. So see in red on the right, I have 2 golds. And we start over again. There's 2 golds in the front and 2 golds in the back. Good. Now pay attention. There's 2 times 3, or 6 chlorines in the front. I only have 2 chlorines in the back. 6 in the front, 2 in the back. How am I going to get 6 chlorines in the back? I have to put a 3 in front of the magnesium chloride. 3 MgCl2s means 3 times double chlorine, or 6. So let's start over again. There are 2 golds in the front, 2 golds in the back. There are 6 chlorines in the front. There are 6 chlorines in the back. There's 1 magnesium in the front, but there are 3 in the product. How am I going to get 3 magnesiums in the front? I'm going to have to put a 3 in the front. Now, one more time, we go through it. 2 golds in the front, 2 golds in the back. 6 chlorines in the front, 6 chlorines in the back. 3 magnesiums in the front, 3 magnesiums in the back. It's balanced. It's in a 2 to 3 to 3 to 2 ratio. John Dalton's happy. I'm happy. You should be happy too. And there is Mr. Farrell. He's happy as well. They always balance. If they don't balance, there's only 2 things wrong: what you're thinking or what you're writing. You must write the formula correctly, and then you have to think and count and keep going back to the beginning over and over and over to get them correct. Copper Roman numeral 2 sulfate solution with silver metal. This is number 5. Copper Roman numeral 2. Put your finger in box 29 on the periodic table. Copper makes either +1 or +2 cations. Here it's the +2. So if we have a +2 cation, now we got to figure out what the heck sulfate is. That's on table E. Sulfate is a polyatomic anion, SO4, with a -2 charge. So if we have a +2 cation and a -2 anion, that's going to be in a 1-to-1 ratio, and it's a solution, so it's aqueous. Silver is a metal. So when we write the original skeleton for the reactants, it's CuSO4 aqueous plus silver solid. Here we have atoms going into an aqueous ionic solution, the setup for a single replacement. Now, when we look at table J, we know that copper and silver are both metals. They're both on the left side of the table, but copper is higher than silver. Silver is lower than copper. So when silver goes into the solution, silver cannot bump out the copper. Cannot. Silver is not as reactive as copper. Copper is more reactive than silver. And the rule is the more reactive atom goes into solution, or the more reactive element stays in solution. In this case, copper is in solution and it's more reactive, so it stays in solution, and we end up here again with no reaction. You must write the formulas for the reactants, put in the arrow, and then say nothing happens. You can't just skip this and say no. You have to write the formulas correctly. You must show that you're thinking and you're paying attention. Number 6, bromine, which is a liquid, because here it is a liquid at room temperature, is going to go into something called ammonium iodide solution, which is aqueous. That's what a solution is. Now, bromine is a Hunkelbrief twin, Br2, and it's got an L with it because that's the phase. It's liquid. And it's going to go into an aqueous solution called ammonium iodide. Ammonium is on table E. Ammonium is a +1 ion on table E. You can just put your finger in the box, and there it is, NH4 with a +1. Iodine is element 53. Put your finger in the box. Iodine is in group 17, and it makes a -1 ion. So if you have a +1 ammonium and a -1 ion for iodine, it's going to go into a 1-to-1 ratio, and it's going to look like this. Br2, which is a liquid, and then in a 1-to-1 ratio, ammonium iodide. Now, when you look at table J, and you have to, because it's a setup for a single replacement, atoms, in this case diatomic atoms, go into an aqueous ionic solution. As it turns out, bromine is higher than iodine on the right. Ammonium is not on table J, and that's fine. The other two, bromine and iodine, are on one side of the table, and in fact, bromine is higher. So here, the bromine is going to replace the iodine. Bromine makes a -1 ion. It's in group 17 also, so it's going to form into ammonium bromide in a 1-to-1 ratio, and the iodine's going to pop out. Iodine's a Hunkelbrief twin. So when we write this, the ammonium bromide is going to be the new solution. We start with the solution, we end up with a different solution. And in this case, iodine's going to pop out as solid. It's going to be I2. Now we have to balance it. So let's start talking our way through the balancing now that we've written the skeleton correctly. There's 2 bromines in the front, but there's only 1 bromine in the product. To fix that, I have to put a 2 in front of the ammonium bromide, and I have to keep going. So on the second slide, I show there's 2 bromines in the front, and now I have 2 bromines in the product. But I have 1 ammonium in the reactant side, but I have to have 2 ammoniums in the product. That's not good. So the only way to fix that is to put a 2 in front of ammonium iodide, and then I have to start over again. So look what I did. Bromine, there's 2 bromines in the front, there's 2 bromines in the back. Now I have 2 ammoniums in the front, and I have 2 ammoniums in the back. That's good. And in the front, I have 2 ammonium iodides, which means I have 2 iodines. Look in the back, I already have I2. This is balanced. It's in a 1 to 2 to 2 to 1 ratio. I'm happy. Bobby McFerrin is happy. You remember this guy? Don't Worry, Be Happy? That's a good album. It's a good song. You know, when he sang all those songs, you remember that song? You probably heard it. You should listen to it on YouTube. The thing that's so cool about his album is all of the sound, all of it, is his voice. There's no music. If you listen to it, it sounds like music. He overdubs and he plays different things. He bangs on himself. He hums low, he hums high. All of the sound on the whole album is just his voice. And sometimes it's overdubbed because it's a little thicker. The music's, you know, multi-tone, but very cool album. It was a very popular song when I was a young man. Don't worry, be happy. All right. Ammonium fluoride solution with chlorine gas. Ammonium fluoride, we're back to ammonium, it's on table E, and fluorine, in this case, makes an anion. Fluorine's element number 9, makes a -1 ion, so ammonium fluoride is going to be in a 1-to-1 ratio, and it's a solution, it tells you, so that's going to be AQ. Chlorine is a Hunkelbrief twin, and it says gas, so we're going to write the reactants properly. It's NH4F aqueous ammonium fluoride solution plus Cl2 gas. Now we go to table J because it's the setup for a single replacement reaction. But as it turns out, fluorine and chlorine are both on the right. Ammonium's not on the table, and that's fine. We have 2 items, fluorine and chlorine both together. But the fluorine, which is in solution, the fluorine is higher than chlorine. So when the chlorine gas is introduced, the chlorine says, hey, I want to go swimming with your ammonium. And fluorine says, you're not strong enough to bump me out of this solution. You're not reactive enough. So you end up here again with no reaction. One more time. You have to write the formulas correctly for the reactants. Then you put your X in. You can't just skip and say, that's nothing. You have to show this part as well. Number 8, lithium hydroxide solution. So that's aqueous, and titanium metal. Now, lithium is element 3. Put your finger in a box. Lithium makes a +1 ion. Hydroxide makes a -1 ion. That's on table E. So the formula is going to be LiOH, aqueous, and titanium is metal. It's element number 22. So this is what it's going to look like. Lithium hydroxide plus titanium metal arrow. Now, obviously, titanium's a metal. Its atoms going into an aqueous solution, the setup for a single replacement reaction. But as it turns out, lithium is a metal and titanium's a metal. They're both on the left. But lithium is literally at the top of the list. Nothing bumps lithium out of the way. So when you put titanium into this lithium hydroxide solution, nothing happens. Nothing happens because the titanium is lower than lithium. Titanium is not reactive enough to bump the lithium out. And this was easy. You write it, you look at table J, and the answer practically bites you on the leg like a little dog that's mean, right? He's a good-looking actor, right? It's not too easy, is it? I hope not. Barium hydrogen carbonate. That's a mouthful. Barium hydrogen carbonate and lithium metal. Now, barium is element 56, and if you put your finger in the box, element number 56 makes a +2 ion. Hydrogen carbonate, that's a huge name. That's on table E. HCO3 is a -1 ion. So it's going to make a fancy formula. See that fancy with the parentheses? That's because you need a parentheses in the formula. And then lithium is just a metal, element 3. So look what we got. We got barium, 1 barium and 2 hydrogen carbonates because it's a positive 2 cation and a negative 1 anion. So you have to have the parentheses because there's 2 hydrogen carbonates per barium. Now lithium's a metal, metal's a solid. Now if you put lithium into this solution, we have atoms going into an ionic aqueous solution. It's the setup for a single replacement reaction. And when we go to table J, lithium is the highest metal. It's much higher than barium. Lithium is going to replace the barium. So we're going to have to rewrite it in the products as lithium hydrogen carbonate and barium gets bumped out. But watch what happens. The lithium makes a positive 1 ion. You can't just guess. There's 2 hydrogen carbonates in the front, but lithium bonds with just 1 hydrogen carbonate because lithium's a positive 1 ion, hydrogen carbonate's a negative 1. We're going to have to figure out that double hydrogen carbonate, single hydrogen carbonate by balancing, but we have to write the formula correctly. Barium is not a Hunkelbrief twin, so it just comes out as solid metal like that, Ba solid. And now we have to start talking ourselves through the balancing. So we start in the front. Start saying it with me. I got 1 barium in the front. I got 1 barium in the back. Good. I have 2 hydrogen carbonates on the reactant side, but there's only 1 hydrogen carbonate in the product side. How am I going to fix that? I have to put a 2 in front of the lithium hydrogen carbonate, and then I have to start over again. So here in the next slide, see to put the 2 there in blue on the line there. So we have, start talking again, 1 barium in the front, 1 barium in the back. Good. 2 hydrogen carbonates in the front. I now have 2 hydrogen carbonates in the back. Also good. But I only have 1 lithium on the reactant side, but I have 2 lithiums in the product. How am I going to get 2 lithiums in the front? That was easy, right? I have to put a 2 in front of lithium, and then check. 1 barium in the front, 1 barium in the back. Good. 2 hydrogen carbonates in the front, 2 hydrogen carbonates in the back. Good. 2 lithiums in the front, 2 lithiums in the back. Balanced. This is a 1 to 2 to 2 to 1 ratio. We're all happy. All right? Me, you, John Dalton, Bobby McFerrin, everybody's happy. Number 10, potassium sulfate solution with lead metal. Here again, we have an aqueous solution with metal atoms going in to set up for a single replacement. So we have to write the formulas for potassium sulfate. Potassium's element number 19. Put your finger in the box. Element 19 makes positive 1 ion. Sulfate's on table E. We've seen it a couple times now. SO4 minus 2. So when we crisscross that, potassium sulfate, we're going to write that formula, and it's aqueous because it says it's a solution, and it's going with lead metal, so lead will be a solid. So it's going to be K2SO4 because it's positive 1 ion and a negative 2 sulfate. So crisscross, we need 2 potassiums for every sulfate, and lead is a solid atom. So we have atoms going into an ionic compound aqueous solution. It's the setup for single replacement. On table J, the metals are on the left. Potassium and lead are both metals. Sulfate's not on the table, and it doesn't matter, but potassium and lead are both on the left side, the metal side, but potassium is higher. And the rule is whatever element is higher goes into solution, or whatever metal is higher stays in solution. So if it stays in solution, we get no reaction. Okay, bada bing, bada boom. This was easy, right? No problem. All right, this is the last one. Holy smokes, right? Writing formulas is actually more important than balancing. Balancing's easy. Writing formulas is trickier. Aluminum metal is metal, Al, element number 13. It's a solid. It's going to go into the solution called nickel, Roman numeral 2 chloride. Nickel on the periodic table is element number 28. Put your finger in a box. Nickel makes a positive 2 or a positive 3 cation. Which one is it here? Roman numeral 2. That means positive 2. So it's a positive 2 ion. Chlorate's on table E, near the bottom left. Now pay attention. There's a lot of chlorine, oxygen, polyatomic anions. Holy cow, is that a lot? A lot of chlorine, oxygen, polyatomic anions, right? The one we want is called chlorate, ClO3 with a negative 1 charge. That goes with the +2 nickel. So let's write the reactants properly. The aluminum is easy, Al, and it's a solid. If the nickel's a +2 and the chlorate's a -1, we need parentheses, and we have 1 nickel with the double chlorate, Ni, and then ClO3 parentheses doubled. That's aqueous because it's a solution. I told you it's a solution, AQ. Now, aluminum atoms go into an ionic aqueous solution, set up for a single replacement reaction. So let's see if it's going to happen. We look at table J. Aluminum and nickel are both on table J. Aluminum is more reactive than nickel. Aluminum is higher on table J. So the aluminum is going to replace the nickel in solution, and the nickel is going to get bumped out. So let's write the skeleton. Now, this is a little tricky this time because the nickel was a +2 ion. So we needed 2 chlorates. Aluminum makes a +3 ion. And if you have a +3 ion with a -1 chlorate, we're going to need 3 chlorates in the product, Al, and then ClO3 parentheses tripled. It's doubled in the front, it's tripled in the back because you have to write the formula correctly. Nickel pops out as a solid. It's not balanced. So let's go through this. We're going to start talking. There's 1 aluminum in the front. There's 1 aluminum in the back. So far, so good. There's 1 nickel in the front. There's 1 nickel in the back. Also good. But we have 2 chlorates on the reactant side and 3 chlorates in the product. 2 and 3, even, odd. One of them is broken. It's the odd one that's broken. How do we fix it? We double the odd one, and then we start all over. So the first thing we have to do is put a 2 in front of the aluminum chlorate. See that blue 2 there? Now I have to start all over again. I have 1 aluminum in the front, but I have 2 aluminums in the back. That's not good. So how do I fix that? I have to put a 2 in front of the aluminum on the reactant side, and then I have to start again. So I put a 2 in front of the aluminum in the front. Now I'm going to talk my way through this again. There's 2 aluminums in the front. There's 2 aluminums in the back. Good. There's 1 nickel in the front. There's 1 nickel in the back. Also good. I have 2 chlorates on the reactant side, but how many chlorates do I have on the product side? I have triple chlorate, but I have 2 of them. 2 times 3, I have 6 chlorates in the product. I have 2 chlorates in the front. I have 6 chlorates in the back. How am I going to get 6 chlorates on the reactant side? I'm going to have to put a 3 in front of the nickel chlorate so I can end up with 6 chlorates. So if I put a 3 there and I got to start all over again, there's 2 aluminums in the front, 2 aluminums in the back. Great. 3 nickels in the front, 1 nickel in the back. Not great. How do I get 3 nickels in the back? I got to put a 3 in front of the nickel in the back, and now we got to do it again. 2 aluminums in the front, 2 aluminums in the back. Good. 3 nickels in the front, 3 nickels in the back. Also good. I have 3 double chlorates or 6 chlorates in the front, and in the product side, I have 2 triple chlorates, or I have 6 chlorates in the back. Now it's balanced. I'm happy, you're happy, we're also happy, and that's it. Finally, we're done, honestly. Balancing is easier if you write the formulas correctly. If you can't write a formula, you're never going to be able to balance equations, or even if you happen to make them balanced, they're still wrong because you have to write the correct formulas. Chemistry is thick. There's a lot of stuff we learn at the beginning, and then you have to be able to keep doing that. If you still are struggling with formulas, you have to go backwards in the notes, and you have to go figure out what are the ways to write compound formulas. You have to practice them. There's a bunch of homeworks. There's a bunch of slides. There's a bunch of challenges. There's 3 or 4 different slideshows of writing formulas from names or names to formulas. You got to practice that. You have to understand the ions. You have to understand the Roman numerals. You have to understand the prefixes. Although we're not using prefixes here, you have to understand, use prefixes for the molecular or covalent compounds. You have to know what I'm talking about. You can't go forward if you don't understand where we are. And it's only going to get worse. Once you learn to balance equations, then we're going to do stoichiometry, which is moles on one side and the moles on the other side of the arrow at the same time. Remember how we did moles before? We're going to get bigger. We're going to double the moles. We're going to call it a different name called stoichiometry. It's all starting to roll together. Ask for help. Call me up. All right? I'll help you. Peace.